Hi, everybody. So today we are going to be talking about Unit 2, Lesson 2, which is about what's called instantaneous rates of change and tangent lines. Now, in our previous lesson, we talked about average rates of change and secant lines. So in today's lesson, we're going to be looking at a different type of rate of change and a different type of line that we can write the equation of when we have an equation, a table, or a graph of a function. So here are our targets for today. The first target is I can use a variety of notations to represent the derivative of a function. So one of the things we're going to be talking about today is derivatives, and there are several different notations we can use. You need to be familiar with all of them. The second learning target is I can determine the slope of a tangent line and use it to write the equation of a tangent line. So once you have the slope, can you write the equation of that line? The third learning target today is I can apply the power rule. So we're going to be learning something called the power rule. You will be asked to apply it to calculate the derivative of a function. So we're going to learn the notation for derivative. We're going to learn that that is connected to tangent lines. That's why those two things are in the same unit. And then we are going to learn how to use the power rule to actually find the derivative. And then last but not least, I can calculate the derivative of constant functions, sums and differences of functions, and multiples of functions. And these will all kind of be part of learning the power rule, but those are some specific types of functions we will learn about today. Okay, so let's jump in with what is a tangent line. If one of our targets for today is to write the equation of a tangent line and to find the slope of a tangent line, we should start by figuring out what is a tangent line. In geometry, we named any line that brushes against a circle, at one point, a tangent line. So this is an example because it brushes a circle in one point. Now we're going to call any line that brushes against one point of a graph a tangent line. So just like circles are curved, graphs can be curved. If we have a line that brushes against the graph in one point, we call that line a tangent line. Now, when we're talking about tangent lines, what makes them different than secant lines is that a secant line is going to touch a graph in two places. A tangent line is only going to touch a graph in one place. So since using our regular slope formulas that we've always used has required us to have 2 points, we are now going to need a different way to find slope because we're only going to have 1 point. So that's where we're going to start talking about derivatives. A derivative is also known as the instantaneous rate of change. So just like slope and average rate of change were kind of interchangeable, derivative and instantaneous rate of change are interchangeable. The instantaneous rate of change of a function is the slope of a function at a single point. In other words, it is the slope of the line that is tangent to the graph at that point. So just like our secant line, we needed a slope, but we had 2 points. Now for our tangent line, we need a slope. We're only going to have 1 point. And since it's a special kind of slope, we give it a special name and we call it a derivative. The derivative is an equation that we can use to find the instantaneous rate of change of a function, or in other words, the slope at 1 point. Finding the value of a derivative is what we are going to spend the rest of this unit focused on. Now, all of these words mean the same thing. And it's important to know that these all mean the same thing because in the directions or in the question, it could be said in any of these ways. If you're asked to find a derivative, that is the same thing as being asked to find the instantaneous rate of change, which is the same thing as being asked to find the slope of a function at 1 point, which is the same thing as it being asked to find the slope of a tangent line. So derivative, instantaneous rate of change, slope at 1 point, or slope of a tangent line all mean the same thing. Now, the notation for this, because rather than saying all these words, we'd like to have a shortcut. The notation for this looks like this. If we say F and then we put like a little tick mark there, X. What we say out loud is F prime of X, prime meaning this tick mark, and that means the derivative of F. With respect to X. Now, we could also say, like sometimes functions don't use f of x notation. They say like y equals or whatever. We could also say dy divided by dx. Now, if you think back to secant lines, we used to say delta y over delta x for change in y over change in x. By changing it to a d, we're just talking about a really tiny change, which means it's basically 1 point. And so dy over dx is very closely related to that delta y over delta x notation. In words, what we say is the derivative of y with respect to x. Now, we could also say d over dx, and then in a bracket, we could put our function. If we write it this way, what we're saying is we're finding the derivative with respect to x, that's this part right here, of f of x. Last but not least, we can say y prime, that same prime that we use with f of x, it could be y prime or f prime of x. Now, why am I spending so much time talking about notation? Well, the reason for that is that when we are writing our work, when we're showing our answers, or even in the directions, it's going to interchange all of these notations on you. And so you want to make sure that you are familiar with all of them so that when you write your work or when you read the instructions, you understand what it's doing. Now, all of this is leading us up to we need to know how to find derivatives because the derivative is going to be the slope that we need in order to write the equation of a tangent line. So, there are some rules we're going to learn that help us find derivatives. The first rule is what we call the derivative of a constant function. Now, constant means that the value of the function is always the same number all the time. And the rule is that the derivative of just a number is always 0. So, for example, let's say we had the equation s of t is equal to 45. If we were to find the derivative of this, we would say s prime of t, because that little prime means that now we took the derivative. And since 45 is a number, the derivative would just be 0. The next rule we're going to learn is the rule for what do you do if you have a single variable. So how do you find the derivative of a number times x? Now remember, k could be any number. An example would be like 7x, so just a number times x. If you have a function that just says a number times x, then the derivative is just that number. So in this case, if I said y is equal to 7x, we would say the derivative, or y prime, is equal to just 7. Next, we have what's called the power rule. And the power rule is really kind of the main derivative rule that we're going to use, at least for a little while. What the power rule tells us how to do is what do we do if we have x with a power? So you can see here we have a number times x to some power. The rule here is that you take that power and you multiply it by the coefficient. So you multiply, I call it drop it down and multiply, and then you just subtract 1 from that power. Now this sounds more complicated than it really is. Let me show you this in action. So if we say f of x is equal to 7x cubed, then f prime of x, remember prime means the derivative, would be, we're going to take the 3 and multiply by 7, so we would get 21 times x to the power of 2, because we would subtract 1 from the power. So I like to say drop it and then subtract 1. Last but not least, what do you do with an equation like this one, where we have h is equal to 3t to the fourth minus 7t plus 5? You're adding and subtracting a bunch of terms that all align with one of these functions. You'll notice the first term would be a power rule term, the second term would be a single variable term, and the last term would be a number. Well, the answer is you just take the derivative of each term one at a time. We call that differentiating. If we ever say differentiate, it means take the derivative each term separately. So in this case, I would say, and I'm going to show you another notation here. So we've seen like s prime of t, we've seen y prime, f prime of x. Here I'm going to write dh over dt because it's like delta. It's a change in y over change in x, but we're using a d now. So for the first term, I would use the power rule. So I would drop the 4, which means I get 12, t to the subtract 1, so I get 3. For the second term, I would use the single variable rule, which means I would do minus 7. And for the third term, the derivative of a number is just 0, so I wouldn't write anything. So this would be my derivative equation. Now, let's practice finding some derivatives using these rules. So the directions here say find the derivative of the following functions. Find the derivative is, I think, our third learning target, if I remember correctly. So we are going to find the derivative of the following functions. Now we're going to make sure we use the correct notation when we do this. So when I find the derivative of f of x, I'm going to write f prime of x is equal to. Now I'm just going to do each term one at a time. So the derivative of x cubed, the invisible number here before the x is a 1. So when I drop my power, 3 times 1 is 3. X to the, now 3 minus 1 would be 2. So drop it, subtract 1. Next, I'm going to take care of the 6x squared. So I would drop my power, which means I get plus 12. X to the 2 minus 1 is 1. So there's like an invisible one here, but you don't have to write that. For the next term, I would use my single variable rule, which means minus 5/3. And for the last term, since it's the derivative of a number, I would not write anything because the derivative of a number is 0. Now we can do this with all types of different powers. So the next example, the derivative of y, I'm going to write this time as dy over dt. You could also say y prime. It doesn't really matter, just as long as you use one kind of correct notation. The derivative of 0.2 t to the fourth, I would drop the 4, so I would get 0.8 t to the 4 minus 1, which is 3. Then I would have t to the third over 5. I like to rewrite that as minus 1/5 t to the third. So if you ever see like divided by 5, you can rewrite that as a coefficient where it's minus 1/5, which means I would drop my power. So I would get minus 3/5 t squared. For the next term, I just have t. Now the invisible number here before the t is a 1. So if I use my single variable rule, I would do plus 1. And the derivative of negative 9 is 0, so I would not write anything down. Now that's sort of basic derivative rules, but things do get a little bit more complicated sometimes, and there are 2 helpful algebraic properties that will help you so that your problems will become easier because you can use these basic rules. So these are basically ways to rewrite the original problem to make it easier to find the derivative. The first thing I want to remind you of is about negative exponents. So if you have an exponent that's in the denominator, you can rewrite that as a negative exponent, and then you don't have a fraction anymore. The other thing I want to remind you of is what's called rational exponents. Now, rational means that the exponent is a fraction. So for example, in this problem, instead of having a root, like a cubed root x to the fourth, I can actually rewrite that as x to the 4 divided by 3. And the reason I can do that is that whatever number is inside the root, like if it's a third root or a square root, that becomes the number that you're dividing by. So the root is what you divide by to make your fraction exponent. Let's see how that can help us rewrite our problems to make it easier to find the derivative. So at first glance, problem number 1 would look really complicated. It's got fractions, it's got roots, it's got all kinds of stuff going on. What I would suggest here is that the first thing you do before you actually find the derivative is you rewrite the original problem. Now, when I say rewrite, I mean we're not finding the derivative. So this is still going to be f of x, not f prime of x, because we're not finding the derivative yet. We're just rewriting the original. But instead of writing it as 4 over x squared, I'm going to convert that to a negative exponent. So 4x to the negative 2. And instead of writing this as minus 3 square root of x, I'm going to rewrite this as 3 x to the 1/2. And the reason I'm making that a 1/2 is that a square root really has an invisible 2 here, and there's an invisible exponent of 1 here. So that 1 goes on the top and the 2 goes on the bottom because the root is always the denominator. Now, after you rewrite, then you can take the derivative. So we're going to do this one term at a time. The derivative of f of x, I would write as f prime of x. And then I'm just going to go in order. So the derivative of 4x to the negative 2 would be negative 8x to the, and this is where it gets a little tricky, negative 2 minus 1 is actually negative 3. So be careful there because you're doing a negative minus 1. And then the derivative of 3x to the 1/2 would be minus 3 over 2 x to the, now 1/2 minus 1 would be negative 1/2. And that would be your final answer. Now let's look at number 2. So for number 2, again, it looks a little intimidating. We've got roots, we've got negative powers. My first step here would be to rewrite the problem to make it a little bit friendlier. So I'm not taking the derivative yet, I'm just rewriting the original. So I would have y equals 7, and then instead of the cube root of x, I'm going to rewrite that as x to the 1/3. And the reason it's 1/3 is because that little 3 becomes the denominator. Plus 5x to the negative 4th, I'm going to leave just like that because I already can use the power rule there, so I'm not going to need to change anything. Next, I'm going to actually find the derivative. So the derivative of y, I'm going to write as y prime. The derivative of 7x to the 1/3 would be 7/3 x to the, now 1/3 minus 1 would be negative 2/3. Then for the next problem, I would do negative 4 times 5, which is negative 20, x to the negative 5th, because negative 4 minus 1 becomes more negativer, so it's negative 5. Now, these are kind of the basic derivative rules. So we've practiced those rules, but now we need to see how to use those to actually help us with our learning target of writing the equation of a tangent line. As always, when we are writing the equation of a tangent line, we need 2 pieces of information. We are going to need a point that line goes through, and we're going to need to know the slope. In the case of a tangent line, the slope is always going to be the derivative of the function at that x value. So not just a formula for the derivative, but a number that you get by plugging in your x. So let's do a couple examples here. Write the equation of the line that is tangent to the given function at the specified x value. As soon as I see the words write the equation of the line, I know that I'm going to organize my work by writing out point. I know I'm going to write out slope. And then I'm going to leave myself a bunch of room, and I'm going to actually put tangent over here. And that's where I'll put my final answer because I know I'm going to need a little bit of work to make this happen, just from experience. Okay, so for my point, I'm going to need an x and I'm going to need a y. To get the x is pretty straightforward because it actually tells me my x in my problem right here. To get the y, I'm going to plug x into my original equation, f of x. So when I do that, I get f of 4 is equal to 4 to the third plus 6 times the square root of 4. Now, 4 to the third is 64 plus the square root of 4 is 2 times 6 is 12. So I get 76. To get my slope, I'm going to find the derivative equation using the rules that we've already talked about. And then I'm going to plug that same x value into the derivative. So step 1 here is going to be to find the derivative equation. Now it's going to be a little bit easier to find the derivative equation if I rewrite the original a little bit first. So instead of a square root, I'm going to rewrite this as x to the 1/2. Now that's going to make it easier because the derivative here then, I can do just one piece at a time. So I'm going to drop the 3 and subtract 1, 3x squared. Then I'm going to drop the 1/2, which means I get 3 and subtract 1, and I get negative 1/2. So there's my derivative. So I rewrote it, I found the derivative, and now I'm going to plug the number 4 in again. So I'm going to have f prime of 4, which is equal to 3 times 4 squared plus 3 times 4 to the negative 1/2. Now, the arithmetic here can get a little bit tricky, and oftentimes we are asked to do these problems with no calculator. So 4 squared is 16 times 3 is 48. That part is a little bit more straightforward. It's what you do with this 4 to the negative 1/2 that gets a little tricky. So what I want to remind you is that just like if an exponent is in the denominator, we can move it up. If we have a negative exponent, we can move it down. So I could rewrite this as 3 over 4 to the positive 1/2. Now, 4 to the 1/2 is really a square root, so I would have 48 plus 3 divided by the square root of 4, which is 2. So I get 49.5 because 3 over 2 is 1.5. So now I've got my point, I've got my slope, and that means I can put them together and make my tangent line by using point-slope form. So y minus 76 is equal to 49.5 parentheses x minus 4. Okay, let's do one more example with a tangent line. So in this case, it says a little bit of a different type of information. It says, suppose f of 7 is equal to 3 and f prime of 7 is equal to negative 1/2. The directions here say, write the equation for the line that is tangent to the graph at x equals 7. As soon as I see write the equation of the line, I'm going to make a list. Point, slope, and then tangent line. Now, how can I find my point and my slope? I don't have an equation this time. In this case, we can actually use the given information and create our point and our slope. So if f of 7 is equal to 3, that means that the point is 7, 3. And if f prime of 7 is negative 1/2, then that means that my slope is negative 1/2 because f prime means derivative. So the derivative, the slope at 7, is 1/2. That means that all I really have to do here is put those things together and make the equation. So y minus 3 equals negative 1/2 times x minus 7. Now, last but not least, just like we did with our average rates of change and secant lines, we're going to learn one application of instantaneous rate of change. So one common application is that we are often asked to find the instantaneous velocity of an object. Now, just like the average velocity was going to be the average rate of change, the instantaneous velocity is going to be the derivative. Because it's instantaneous of your position function. And just like with average velocity, it's still a vector. That means your answer can be positive or negative, and the sign of that value indicates the direction the object is traveling in. So let's say we're given the position of an object above the ground is given by the table of values below. Estimate the velocity at t equals 4. Now, this is a little different because instead of being asked to find the average velocity between 2 points, we're asked what is happening at 4. Now, the number 4 lives in between the numbers 3 and 5. So in order to estimate what's happening at 4, we're going to do our best, which is the best we can do is find out what's happening between 3 and 5, because 4 would be in between. So my average velocity, which is going to be the estimate of the derivative, is going to be found by doing our change in position divided by change in time. So the change in position would be 45 minus 92, which divided by 5 minus 3, which gives us negative 47 over 2. Now our units here would be feet per second. Now, by contrast, what if I told you that the position of an object above the ground can be modeled by this equation? Find the velocity at t equals 2, which is 1 point in time. As soon as we see that this is 1 point in time, it tells me we need to use the derivative, because the derivative is how we find the slope at 1 point in time. So the first step here would be to find the derivative. So f prime of t equals, to use the power rule here, I would drop the 2, so negative 32t, and you could write to the first power, but it's not really necessary. And then the derivative of this single variable function would be plus 12, and the derivative of 200 would be 0. So that's my derivative equation. The second step here would be to plug in the number 2 because it asks me specifically what's happening when t is 2. Which means I'm going to get negative 64 plus 12, which is negative 52. And that's going to be measured in feet per second. Now, what I want to point out to you here is, what do you notice about using the average velocity to estimate the instantaneous velocity? So how does our estimate compared to the actual? The answer is they're both negative. So they both have the same sign. But the values are wildly different. So finding our average velocity is not going to be the same thing as how fast are you going at a single moment. All right, well, thank you guys so much for watching. That's the end of this video. I hope that you have a great day, and I will see you in class for some practice.